It's my pleasure to be here to talk about our research on in-network computing. So I've heard of lots of interesting projects in the Crossroads 3D FPGA Research Center, and I think they fit very well in a broader view of in-network computing. So today, what I'd like to share with you is some of my thoughts on interesting problems and challenges in pushing the limits of today's in-network computing and some of my recent work on solving these challenges. So when we took computer networking course, we saw a network topology looking like this. So at the edge of the network, there are many end hosts, such as your laptop computers and servers, equipped with network interface card or NIC. And at the core of the network, we have a collection of routers and switches that allow end hosts to communicate with each other. In this traditional view of the network, these switches and routers and NICs have fixed function, which is simply forwarding data or packets from one point to the other. However, this simple traditional view of the network is not valid anymore. Today, especially for the last 5 to 6 years, network devices become more programmable so that they can not only just forward packets, but also perform some computation on moving data. A key enabler for this is a recent advance of programmable switching ASICs and FPGA or NPU or ASIC-based smart NICs, which can process packets at high speed while executing some stateful operations for each packet. This technology advance creates a new computing paradigm called in-network computing. By leveraging the ability to execute some operations on moving data inside the network, in-network computing allows us to offload tasks traditionally running on end-host CPUs to the network devices to save precious CPU cycles. In fact, many recent works have shown the feasibility and performance benefits of various applications running on these devices, including canonical middlebox functionality such as firewall and load balancers, and more innovating use cases such as DDoS defenses, in-network aggregation for machine learning tasks, and so on. So why do people care about in-network computing today? We have observed that it's mainly because applications demand and the technology trends have converged in a very timely manner. In particular, today, while network bandwidth is growing rapidly, for example, 70% for every year, the speed of CPU performance improvement has decreased. This can cause high and unpredictable application performance, such as high tail latencies. Thus, application developers and network administrators want to solve such performance issues in a cost-efficient way. On the other hand, as I mentioned earlier, network devices, especially their data plane, become more programmable with no or little performance impact. For example, recent programmable switching ASIC can support up to a few terabit per second of packet processing speed while performing a limited set of computation on each packet. Since such network devices can process data at high speed and provide predictable low latencies, in-network computing becomes a potential solution to the performance problem in the data center. So given these users' needs for high performance, the technology advances now create many new opportunities. Let me give you one concrete example of in-network computing application that we have built, which is in-network DDoS defense system. Here, our goal is to block attack traffic inside the network while not affecting benign traffic. And our approach is to deploy defense functionality on programmable switches. While we are building this system, we observed its 3 defining characteristics. First, the first characteristic is that the attack vectors become diverse, meaning that we need to run multiple concurrent defenses at the same time on a switch. The second observation is that both the number of attacks and benign and attack traffic flows increases, which makes defense function resource intensive. Lastly, these defense functions are stateful, so losing the state due to device failures become critical. While I use in-network DDoS defense system as a concrete example, in fact, these are general trends in in-network computing applications. So to implement such an in-network application, ideally, developers write application code with an illusion of infinite fault-tolerant resources on switches. And then the underlying platform seamlessly supports multiple applications with elastic resources while effectively handling device failures. However, today we are programming the network devices like people did in early days in computing, like in 1960s. There's only a single program running on a single device, and you have to write a program using a very low-level abstractions with very constrained resources available on each device. You don't consider device failures as well. So essentially, in today's in-network computing platform, there's no notion of multiplexing across multiple apps, no elasticity for compute and memory resources, and no resiliency against the device failures. In fact, what we really need is operating systems like abstractions for in-network computing. If you look at these OS and distributed systems literatures, they already provide abstractions for resource elasticity and for tolerance, which are exactly what we need. For resource elasticity and multiplexing, we have a virtual memory abstraction, which provides an illusion of large resources, large memory resources for each app. And for tolerance, we have several mechanisms such as replicated state machine and external state store, which provides an illusion of a single highly available system. Then our question is, can we have such abstraction for in-network computing, or can we apply such existing mechanisms to in-network computing platform? Unfortunately, it turns out it is not trivial to enable such abstractions in our context. While the virtual memory or virtual resources are designed based on a hierarchy of resources, in our context, we only have fixed and limited resources on each device. It is hard to elastically extend resources and capabilities in the first place. And due to the limited programmability based on low-level primitives, it is very hard to implement the existing mechanisms in our context. And lastly, even if we can somehow implement them, since it operates at much higher speed than CPU servers, such as terabit per second, it is hard to meet performance requirements if we just follow the existing designs. Fortunately, we find an opportunity for the first challenge of fixed and limited resource, which seems to be the most fundamental one. If we look at outside a single device, in our case, a switch, there are available external resources we could leverage. For example, on CPU servers, we can find tens of gigabytes of DRAM with much higher flexibility. And on the smart NIC side, we have a few gigabytes of DRAM or like HBM with a higher flexibility. Then our question is, how can we effectively leverage these external resources on data plane devices? So our approach to realize it is designing high-level abstractions and corresponding runtime environments for resources on heterogeneous external data plane devices to enable elastic and resilient in-network computing without any hardware modification. Especially, we argue that we can make network an elastic and resilient computing platform with the right abstractions for resources available on heterogeneous data planes and with a runtime environment. Under this high-level approach, we designed 3 systems that propose a defining abstraction and runtime environment. The first work, which is T, provides elastic memory with an illusion of a large match action tables for network functions running on programmable switches. And ExoPlane extends this approach to make compute resources elastic as well. And lastly, RedPlane shows how to make in-network applications tolerant to device failures by providing an illusion of a single highly available switch. In this talk, I'm going to focus on T and discuss briefly 2 other systems later. Before I jump into T, is there any questions about this high-level approach and general background questions? Okay, so Yes, since programmable switches provide predictable high performance at lower cost compared to other mechanisms to implement network functions, they became an attractive platform for various in-network functions, including middle box functionality, such as network address translator, load balancer, and firewall. However, we observed that switch-based network functions cannot serve very demanding traffic workload. An example of such demanding workloads would be a workload that consists of tens of millions of concurrent flows with a terabit per second traffic rate. And we observed that a single programmable switch cannot maintain necessary flow state for a large number of flows. And the key reason for this is limited SRAM space on the switch, which is tens of megabytes. Since SRAM is generally very expensive, just adding more SRAM cannot be a good solution. So instead, in this work, we try to tackle this problem by answering this question. Can you leverage larger and cheaper external DRAM that already exists via the switch ASIC? To answer this question, we developed table extension architecture, or T, for programmable switches. We build on our observation that there's a bunch of DRAM available on remote commodity servers connected to the switch. Essentially, T provides network functions or other in-network applications with a virtual table abstraction that creates an illusion of large lookup table using external DRAM on servers. And T provides an API that allows developers to easily enable T in their NF implementations. It also provides low and predictable lookup latency with scalable throughput. At a high level, to use T, developers implement their NFs with T API and P4. P4 is a domain-specific language for these programmable data planes. Then they compile it with an unmodified P4 compiler, vendor-provided P4 compiler, which gives them with binary loaded to the ASIC. And at runtime, while the application running on the ASIC processes packets as usual, T allows it to access lookup tables from either on-chip SRAM or external DRAM on servers. While this idea of using external DRAM sounds simple, we had to address several challenges to realize this approach. When a packet comes into the pipeline and there's no table entry for the packet in SRAM, the ASIC needs to access the table on the server. To achieve this, the ASIC can access the DRAM through the control plane, the switch's control plane. So the CPU on the control plane and the server establishes a connection. And the control plane CPU retrieves an entry from remote DRAM through a traditional RPC-like mechanism. But in this control plane-based approach, DRAM access approach, due to the CPU involvement of the control plane and the server, it can incur high and unpredictable latencies, which can affect the packet processing performance. And also the access bandwidth between the ASIC and the control plane, as well as the control plane and the server, is limited by hardware design. So we need to design DRAM access channel that enable direct memory access from ASIC without involving the CPU and also without hardware modifications. We designed the memory access channel based on RDMA, remote direct memory access, or RDMA, which is known to provide an remote memory access capability with low and predictable latencies without CPU involvement. Sorry. So our key insight here is that when the RDMA is deployed on the Ethernet, in like data center Ethernet, RDMA request and response packets are just Ethernet frames, normal Ethernet frames, meaning that these Ethernet switches, programmable switches, can understand RDMA packets without any spatial built-in RDMA capability if we can give some information about how the packet look like, how the RDMA packet look like. So based on this insight, we leverage the programmability of the ASIC to craft RDMA request and parse the RDMA response on demand so that we can leverage the RDMA capability on the server side to access the remote DRAM. So let me explain how it works using an example. When a packet comes into the ASIC's pipeline, the ASIC adds RDMA protocol headers to craft an RDMA write or read request. I'll explain later when we need write or read request. Then the server's NIC will response it with an RDMA response packet as it would for any standard RDMA request. In this step, since the RDMA capable NICs attached to the server processes the request, memory access request, there's no server-side CPU involvement. Then the ASIC can parse the response as a normal packet. One thing we need to consider here is to prevent possible RDMA request loss at the NIC. To do this, we employ a simple switch side flow control without implementing a full stack RDMA functionality. With our direct memory access capability, now we have to think about how to use it for actual table lookups. Although our RDMA-based channel provides a low and predictable latencies, from our measurement, we observed that it still takes around 2 microseconds. So if a table lookup operation involves multiple memory accesses, it could again result in high and unpredictable per packet processing latencies. So our question is, can we devise a remote table lookup mechanism that takes at most a single round trip or that supports constant time table lookup complexity? The most common solution used for constant time table lookup within a switch hardware today is Cuckoo hashing. So we started from Cuckoo hashing as a potential solution, and so how it would work in our context. In the two-way Cuckoo hashing, for example, when we look up an entry with a key, such as IP5 tuple, there are 2 candidate buckets where the value for the key can be located, which means it requires 2 memory accesses to retrieve a correct table entry. However, while SRAM in a switch supports parallel memory accesses for such table lookups, it is hard to efficiently support it on DRAM, especially through the RDMA channel. So we need an alternative that can enable table lookups with a single remote memory access. To this end, we devised our data structure called T-table, which is designed based on prior work called bounded linear proving, or BLP. So BLP was originally designed for improving cache hit rate in software switch, and we repurposed its way of placing buckets for a given key in a hash table. So unlike traditional Cuckoo hashing, BLP puts 2 buckets in a conjugative memory regions. To do so, it trades some amount of space efficiency for a contiguous bucket allocation, which works well for our needs and in our context. This contiguous allocation allows us to retrieve 2 buckets in a single RDMA read. Then the ASIC can parse entries in those 2 buckets. Also, it significantly simplifies our insertion and deletion logics as well. Now, while the ASIC can do table lookups with our T-table structure, the ASIC must be able to process packets with retrieved table entries, such as an address mapping in NAT. This means that during the table lookups using external memory, it needs to somehow hold a packet so that after the table lookup completes, it can use the retrieved table entry for processing that specific packet. However, today's switch architecture does not allow buffering arbitrarily packets. And even if we could somehow buffer the packet at the switch, it can consume an excessive amount of switch's packet buffer, which is undesirable. So we need to enable deferred packet processing or delayed packet processing without stalling the entire pipeline and without consuming a large amount of switch's memory. So I'm not going to the details of this solution, but the key idea is to employ a scratchpad, which is the additional temporary region in the T-table to temporarily buffer the packet, so that when the switch ASIC reads the packet and the bucket, 2 buckets from the T-table, it can read this whole entire region from the T-table structure and then parse it and process this original packet, piggybacked packet using the retrieve key. I retrieve the bucket from our key table. So far, I've explained a basic design of T with a single server. As mentioned earlier, we could improve the performance and availability with multiple servers, but there are some challenges to achieve that. So I'll just briefly mention our high-level ideas to address them. One is we employ a small on-chip cache, which contains a few frequently accessed table entries to balance memory access loads across multiple servers, as well as scale out the throughput. And to react servers availability changes fast, we repurpose ASIC's capability, including event-based packet generation and meters. So putting pieces all together, T provides a virtual table abstraction to in-network applications so that they can have an illusion of large lookup tables. To achieve that, we leverage ASIC's programmability to enable direct remote memory access via RDMA purely in the data plane. And we repurpose BLP to devise an efficient data structure, table data structure that allows table lookups in a single round trip. And we also offload the packet store to T table so that we can enable delayed packet processing. And finally, we employ a small on-chip cache to support higher throughput and for better utilization of multiple servers. We implement T API and Runtime as modules in P4 so that developers can easily enable T with their NF implementations. Using this API, we implement canonical network functions, including NAT and stateful firewall. And we evaluate T using a testbed consisting of a Tofino-based programmable switch and a number of servers with RDMA. So to evaluate this, our first question is, how does T affect processing latency of a network function? To evaluate this, we measure the distribution of per packet processing latency of NAT, network address translator, by using a set of packet traces, including both synthetic and real traces. And for synthetic ones, we generate traces with different flow size skewness because it can affect the cache hit rate and the latency distribution. And we compare it against the baseline, which only uses switches SRAM, on-chip SRAM, without accessing the external DRAM. Here, the x-axis is the latency and y-axis represent the CDF of the latency. So this is the distribution of the baseline's latency, which takes only a few hundreds of nanoseconds. And this is the result for T-enabled NAT. Basically, the distribution is divided into two parts. The left-hand side is the distribution, latency distribution when the lookup is served by on-chip cache. And the right-hand side represent the case where lookup is served by T-table on external DRAM. And we can see that for more skewed traces, they have higher chances of being served by on-chip cache. And regardless of the skewness, we see that the variance is small, which result in predictable end-to-end latency. Next, we measure the throughput that T-enabled network function or applications can support with a different number of servers. And again, we use T-enabled NAT as an example. Here, the x-axis is the number of DRAM servers and y-axis is the throughput in million lookups per second. We can see that the throughput can be scaled by adding more servers. And also we can see the on-chip cache actually helps improve the throughput a lot. So after the publication of this work, there have been some interesting follow-up work based on T. On the application side, I have been collaborating with Intel and AT&T to build scalable user plane functions, which is one of the network functions in 5G cellular networks that can handle billions of user devices. Also, there's an interesting work that leverages T's approach for collecting network telemetry data in cloud data centers. In that case, the switch uses remote NVMe storage as external persistent storage, and they access that storage through RDMA. And on an architecture side, we heard that Intel adopts T as a reference design for their next generation switch-centric platform with FPGA as an external resources. And also we are exploring a potential integration with processing in memory technology, in such a next generation switch-based platform to support more advanced and complex applications. So far, we've seen how T can make network memory resource elastic for a single memory intensive application using external memory. Now, I'll briefly describe ExoPlane that provides elastic compute and memory resources to support the multiple concurrent applications on a switch. As a concrete example, we try to run the 4 applications in data center scenarios, but varying the number of concurrent flows per application, or fixing the number of flows to 1 billion, but adding the apps, number of apps incrementally. And we measure the SRAM requirements from each app and normalize it to the total amount of SRAM available on a switch. So we can see from this figure that as the workload increases, it becomes infeasible to run all the apps. And on the right-hand side, we also see that the switch can support only a single application when the workload, I mean, the size, the flow, the number of flows required by each app is large. And in this case, the root cause of this limitation is a constrained amount of switches SRAM space. So to solve this problem, we designed ExoPlane, which is an operating system for on-rack resource augmentation architecture. So in this rack scale or rack level architecture, a switch is directly connected to a smart NICs equipped with compute and memory resources. And ExoPlane enables the applications designed for switch to leverage resources at runtime while hiding the complexities of accessing external resources and scheduling scheduling various tasks. And it consists of 2 key components. One is ExoPlane Planner that takes multiple P4 applications written for a switch with no or little modifications and optimally allocates resources to each app based on the input from network administrators and developers. And the second component is ExoPlane runtime environments that executes workload across the switch and the external devices by correctly managing the state, balancing the load across the devices, external devices, and handling device failures. So with these 2 components of ExoPlane, network operators can run multiple concurrent applications on this platform, on this rack scale platform, without handling the complexity. While T and ExoPlane enable multiple concurrent in-network applications, if your switch or other device fails, your stateful applications will lose the state and either affect the performance or correctness of the applications. And our RedPlane work addresses this by providing an illusion of single highly available switch abstraction. Let's take a look at an in-network NAT as an example. So suppose that the NAT has been deployed at 2 switches in the network. Initially, this red flow is routed to and processed by this NAT1 instance. Now, the switch running the NAT1 fails. And since today's networks are typically engineered to mask such a link failure, network failure, by providing redundant path, the upstream switch can route the flow to an alternative switch. So packets now arrive at the NAT2, but since this NAT instance does not have the flow state, packets cannot be processed and the connection will be broken. So while I use NAT as an example, switch failures can lead to incorrect behaviors of various in-network stateful applications, including other stateful network functions. Indeed, recent measurement studies in production network have shown that the switch failures are common in practice. So we designed RedPlane which provides a fault-tolerant state store abstraction for in-switch applications. Essentially, RedPlane provides in-switch applications with a one big fault-tolerant switch abstraction by leveraging an inexpensive replicated state store implemented on commodity servers. For developers, it offers an API to easily enable RedPlane in their applications and provides a protocol that correctly replicates the application state entirely in the data plane. After this work, we are adopting RedPlane's approach to protect our in-network functionality running as part of 5G radio access network from switch failures. So far, I've described 3 systems we developed to make network as an elastic and resilient computing platform. So how do these systems work all together? Let me explain it using our DDoS defense as an example again. So we built a small cluster consisting of 2 programmable switches and a number of smart NICs and servers. Developers write defense functions such as synproxy, DNS verifier, or NTP verifier in P4 with T or RedPlane APIs. And the network administrator provides device and application information, application-specific information, and objective functions for ExoPlane Planner, which loads these applications to the platform, to our rack scale platform. And then ExoPlane, T, and RedPlane runtime environment will schedule the task and handle failures at runtime. So while we demonstrated the feasibility and practicality of our approach in the course of our research, I think it's really scratching the surface in this area of in-network computing. So before closing the talk, I'd like to spend next couple of minutes to discuss what should we do next. When we consider deploying in-network functionality in production networks, the major roadblock is guaranteeing its reliability. So reliably deploying and managing in-network applications is challenging today due to the scale of the network and the diversity of programmable hardware devices existing in the network. And it makes it difficult to deploy multiple applications safely, manage state shared across multiple devices, and also it is difficult to manage hardware interoperability. So basically, the network now becomes a large-scale distributed systems running on diverse set of hardware. And to address such challenges, we need to rethink about a way to deploy new in-network application without affecting existing applications with correctness and performance verification. Also, managing resources and states at runtime on multiple heterogeneous devices will be an interesting problem to solve. And I think revisiting existing approaches and techniques developed in the context of distributed systems, programming languages, and software engineering, and applying them in this context will be a potential direction we can pursue. And in the course of our research, we observed that there's a critical missing piece which is an ability to reconfigure data plane functionality at runtime, especially without downtime. So today it takes several seconds to minutes to reconfigure a programmable switching ASICs or FPGA, which leads to significant downtime of applications. Since in-network computation happens on the critical data path, fast reconfiguration, the fast runtime reconfigurability is essential. So if we have such an ability, it will be a key enabler for several use cases, including adaptive in-network functionality such as DDoS defenses for time-varying attacks, and zero downtime maintenance of the devices. And perhaps it could be used to enable multi-tenancy for in-network computing. To realize this, I think the hardware and software co-design approach is necessary. First, we need to design a new data plane architecture that supports stateful applications perhaps by leveraging existing partial reconfiguration designed for FPGA. And we need to rethink corresponding programming language, programming abstraction, and APIs that hide the underlying complexity of runtime reconfiguration. So to conclude the talk, with the recent technology advances, in-network computing becomes a reality, and it creates many new opportunities. At the same time, we observe that resource elasticity and fault resiliency are key missing pieces today. And to address these challenges, I was talking about our research on making in-network computing elastic and resilient. And my broader research vision is to make the network as a future-proof computing platform. And I think it's a good time for us to rethink abstractions and hardware designs for better and practical in-network computing for the future. I hope this talk can spur some interesting discussion and potential collaboration opportunities. With that, I'll stop here and happy to take any questions. Thank you.